Hey guys, wanted to get together, work some problems today. These are just little sample problems. They will look something like what I'm thinking about for the test. Not the same questions, but the same concept, same level, and just to give you an idea of where this is going and make sure that you are ready for this, okay? Here's the first one. I'll try to clip through these. You're welcome to call me, text me, email me with questions, and if it doesn't quite make sense, but I'll try to show what I'm doing here. Right here I'm going to pull some heat. I'm removing heat. Now normally we're adding heat, but it works the other way too. We want to take this 3 kilograms of water at 20 degrees and turn it to ice, or at least some part of it to ice. So the way we usually do this is, kind of draw a little picture and say, here's a puddle. I got 3 kilograms of water. It's at 20 degrees Celsius. And I know I need to cool that off. As I pull heat out, it's going to turn into 0-degree water, and then I can turn it into ice. The only trick here is that it's not going to all turn into ice, right? They're saying what % turns to ice. So while this is 3 kilograms, and it started out 3 kilograms, this is some unknown part that will be 0-degree ice. So there's kind of two transitions here. You could go ahead and find the first one and then see what's left for the second one, subtracting all everything. Or you could write it all out in one fell swoop. Let's do that, just keep it simple. This first, I'm changing temperature, so this is a sensible heat change. And as such, that's going to be an MC delta T here. And this is a latent heat right here, where I'm removing heat and it's changing the state. So I need to put plus. Normally we would put ML, but this is the mass of the water that turns into ice. So let's just call that X or something here to do that. And then we're going to solve for this X right there. You see that I have Q. I've got 3 kilograms. I've got the specific heat of water there. Those constants will be given on the test. I got to drop it 20 degrees. The latent heat right there, 335,000. So I've got everything except for X, and we can just solve for that. I'm going to go ahead and subtract this term from both sides, leaving me with XL. I divide by L, and let me just do that right here in the interest of time and space and everything. There's that X that I need. So right here, I've got 800,000 joules minus 3 kilograms of water, which takes 4,186 joules per kilogram degrees Celsius to change the temperature of. I want to drop it 20 degrees. And then I'm dividing by 335,000 joules per kilogram right there. Alright, that's going to give me X, and what I can do is just punch it in just like you see right there. I'm going to come here and I'm going to put some parentheses around that numerator, hold it all together. There's my 800,000 minus 3 times, didn't get the minus either, minus 3 times 4186 times 20. Close up the numerator and divide by 335,000, and that should be 1.6 kilograms would be the mass of water that turned into ice. They actually ask what percent. So there'd be one more little step here. I changed 1.6 kilograms of 3 kilograms. That's a little over half. And 1.6 divided by 3 would be 54.6%, something like that. Okay, would be the percent ice. All right, great. Let's see what else we got. Here's 4 kilograms of hot copper. We're going to drop it into 5 kilograms of water. And we'd like to know the initial temperature of the metal. So the place I'm going to start this would be the the sum of the heat equals 0. I'm going to have the heat that is lost by the metal, and when I add that to the heat that is gained by the water, it's going to be 0. I do not get any free heat. I don't lose anything. It's all right there. Heat goes from the metal to the water, meets at a common temperature. Nothing is changing state here. The metal started out solid, remains solid. The water started out liquid, remains liquid. So I've got an M of the metal times the C of the metal times the change of temperature of the metal. And then here I have the mass of the water times the heat capacity of the water times the change temperature of the water. That's equal to 0. And we are looking for the initial temperature of the metal. So I'm going to stretch this guy out. The change of temperature of the metal would be the final temperature, let's call that T, minus the initial temperature, the temperature of the metal at the beginning, right there. I think I can just leave all this right here. We'll go ahead and stretch it out, I guess. M sub W, C sub W. That'll be T minus T sub W, like that. And it's all equal to 0. I'm going to subtract this term, put it on the other side, and then we can distribute over here and kind of clean up as we need to. Let's go ahead and distribute. How about that? M sub M, C sub M times T. Then I need to do M sub M, C sub M times T sub M. And I'm going to subtract that term from both sides. So that'll go like that. All right. This is what I'm after right there. So I'm going to subtract this guy off of both sides too. And I'm kind of running out of room here. So you know what? I'm just going to kind of put this from both sides. And it'll cancel here on the left. And we will put it, painting myself in a corner here, but something like that. All right. Now, I want to leave this here. I want to get rid of that. That's all multiplied, so I would need to divide by negative M sub M, C sub M. And I'll do that over here too. I would normally do this with a little more space, but I don't have it coming up fast. So that's going to cancel, and this is going to cancel. There's that T sub M, the initial temperature of the metal that I'm after. And I've got just enough room here to, notice I've got a negative and a negative and a negative, so I could just let the negatives on the top cancel the negative on the bottom, write everything positive. I guess I'll do that. The mass of the water was 5 kilograms. The heat capacity of the water is 4186 joules per kilogram degrees Celsius. And the temperature there, the final temperature was 95. Initially it was 40. So that's a difference of 55 degrees Celsius. Over here, I have the, remember we factored all those negatives out. So this is positive, positive now. The mass of the metal was 4 kilograms. And the heat capacity is given here to be 390. And the final temperature was 95 degrees Celsius. When I divide by, come on, oh wow, by the mass of the metal, so there would be a 4 kilogram, and the heat capacity was 390. Okay. With these, I always encourage you to check your units. So when I'm looking here, I see that there's a kilogram here. I bet it's not going to let me get in there, is it? I'll try. Get that one. Here's a degree Celsius that cancels that one. Nothing but joules right there. Same thing over here. Kilograms, degrees Celsius. I'm in joules. I got energy on top. Joules and joules go together very nicely. Those joules on the top will cancel the joules on the bottom. Like that. And I also have this kilogram. It's going to cancel that kilogram. The only thing left is that degree Celsius right there, and that's on the bottom of the bottom. So that's going to invert up and give me a degree Celsius for the unit, which is good because I'm looking for the temperature of the metal. And all I got to do then is push some buttons, if I can find a place to put this and see everything. Okay, so I'm going to start the whole numerator with a parenthesis here. Make sure that that whole top happens before the bottom. And I've got 5 times 4186 times 55 plus 4 times 390 times 95. Close up the numerator, divide by 4, also divide by 390. And there's 832 point something. Let's call it 833, shall we? Okay. So that's some pretty hot metal there. Remember that water is really hard to heat. It's going to take a lot of heat to raise it from 40 to 95 degrees, just dropping in a chunk of metal. Not even as much metal as you start, with water. So it's going to have to be pretty hot to make that happen. All right. Right here we've got, looks like there's some gas in a gas tank. Fill it all the way up, and it's 15 degrees, and then it goes up to 39. As it warms up, it's going to expand, so they want to know how much is spilled here. So this is a volumetric thermal expansion. Of course, we got a formula for that. Delta V equals V naught beta delta T. All right? And I think we have all those numbers here. V naught would be the 60 liters that we're starting with. The beta is given right here. 3 times 10 to the negative 4 per degree Celsius. There we go, sorry. And what's it do? It goes from 15 to 39. That would be 24 degrees Celsius. And you punch that in. That's not a big deal. You'll get the number there. Now that's if the tank does not expand. I guess we'll go ahead and get a number there, but you can see where that's going. 3e negative 4 times 24. Okay, 0.432 liters. I'm just leaving that in liters because that's what they gave it to me in. Okay, but it would look something like that. Now, if you wanted to know, well, the tank is metal, let's say, it's going to expand too. So then what you need to do is say, well, the gas expanded this much, but the metal also expanded. So it would be the difference between those two. This is just the gas. But I could come in here and find the expansion of the tank and do the same thing. I got a 60 liter tank. I'd have a different coefficient of thermal expansion here because it's a different metal. It's not gasoline, it's steel. And I believe that number is 36 times 10 to the negative 6 per degree Celsius. You can see that that's a lot smaller number. So the tank will expand some, but nowhere near as much gas, and you're still going to end up with spilled gas. That was a real thing back in the day. You didn't ever want to top your gas off. They've got some kind of tubing system now that prevents it. I can't remember. But spilling gas is all of a sudden is a no-no, so they figured out a way it wouldn't do it. 0.05, let's call it 0.052 liters, is the expansion of the tank. So if you wanted to know how much spilled, even if the tank expanded, then you'd want to take the difference of those two. Alright, so 0.432 liters is what would have spilled, and now my tank got a little bit bigger, so it's going to hold that much of it, and you could take the difference there and see what that is. Alright, how much work is done by an ideal gas expanding from a volume of 3 liters to 30 liters. So I'm going to just make a little note here for myself. The volume is going from 3 liters up to 30 liters. And there's a constant pressure. That's interesting. I know that when there's a constant pressure, that has a special name. That's an isobaric process. And since I'm looking for work here, I'm kind of trying to nail this down to one of my 4 processes. Is it isobaric, isochoric, adiabatic, isothermal? What's really happening here? So here's pressure and volume. It's an isobaric process. I know in an isobaric process that the work is equal to the pressure times the change in volume. So that's where we want to go here with this one. The only real trick is these are not proper units, right? Liters, we don't work in liters, we don't work in atmospheres. So I do have to do a little bit of conversion here. We like cubic meters. What I'd have to do is say that there are 1,000 liters in a cubic meter and set that up so that it cancels, and then I've got 0.003 cubic meters is my volume. Forget about the, you know what I did, I messed this up. The change in volume is what I should have done. So let me put a little delta V. 30 to 30, 3 to 30 would be 27. So let me put that 27 right here. And when I move the decimal place 1, 2, 3 times, then I will get well, that didn't do a very good job, did they? I need my money back for that. Oh, there it went. It just faded away. 0.027 cubic meters would be delta V. And then the pressure is 2 atmospheres, but we don't even like that. The pressure is equal to 2 atmospheres, but we don't work in atmospheres, we like pascals. So I need to know, actually it should be on the test somewhere, that 1 atmosphere is 101,300 pascals. This is a measurement of atmospheric pressure in atmospheres. This is atmospheric pressure in pascals. You can use that like a conversion factor. And I've just got to multiply this by 2, so that'd be 202,600 pascals. And those are the numbers that I want to stick in up here. So I got 202,600 pascals times 0.027 cubic meters. Checking the units there, remember that a pascal is really a Newton per meter squared. So I'm going to scribble this out. The meter squared on the bottom is going to cancel 2 of these meters. So this cancels that. And now I've got a Newton meter. A Newton meter is a joule. And a joule is a perfectly good measurement of work. So we are happy there with that. 202,600 times 0.027 would be 5,470 joules right there. Most people get this part right, but then they, not most, but a lot of times they'll just put in 27 and 2 and get 54, and you can see that there is a 54, but it's 5,400 and change. So be careful with the units. The units on this test are probably the trickiest part of the whole thing. Make sure that you're working in the right units. Right here I have an engine that's 40% efficient, does 3,000 joules of work as it operates between 2,000 K and 300 K. Now those are the temperatures. This would be the hot temperature, and this is the cold temperature, and those are already in Kelvin. That's good. If they weren't in Kelvin, we'd have to put them in Kelvin. Remember how some things have to be done in Kelvin? This would be one of them. They're asking us 2 questions. How much heat was required, and what is the ideal perfect Carnot efficiency? So I'm going to draw a little line right there. And we did 3,000 joules of work. You could come in here and, what's the easiest way to do this? You know that the Q equals the change in energy plus the work, right? So Oh yeah, and even better, I'm sorry. Let's go here with it. The efficiency equals how much work I get out versus how much heat that I put in. Basically, we're saying that 40% of it went here, and 60% went into the change of internal energy. But since they gave us the efficiency, let's start here. We want to know the heat, so I'm going to do the swappy thing here and say Q equals work divided by efficiency, and that would be 3,000 joules divided by 0.4, changing the percent into a decimal, and I don't know, some kind of number. 3,000 divided by 0.4 is 7,500. That makes sense. If I got 3,000 joules out, and that was 40% of everything I put in, then I'd have to have a whole bunch more. So I put that much heat into it. I paid for 7,500 watts of heat, and that accomplished 3,000 joules of work for me. So that's the answer to the first question. The second one here, what would the ideal efficiency be, or the Carnot efficiency? Remember that we had a second efficiency thing. This is the absolute efficiency, if you will. The ideal efficiency, just kind of a ballpark figure to say what's the best we could ever hope for out of this, was 1 minus T sub C over T sub H, the cold temperature and the hot temperature. So that's why these numbers are in there. And those do have to be in Kelvin, so be careful there. But here we're okay. And we could just come in and say 1 minus 300 K over 2000 K. And this will give us the best possible number that we could ever get out of this machine. And 1 minus 300 divided by 2000 is, do something up there. What messed up? Oh, yeah. That would do it, wouldn't it? I got 2 subtractions. Tell you what. Trying to do it on the keyboard instead of, there we go, 0.85. Okay, 0.85 is a decimal. Usually we express efficiencies as percent, so that 0.85 would be equal to 85%. In a perfect world with no friction, no air resistance, no loss of heat, anything, if everything was perfect, we could only get 85%. Well, we only got 40%, so there's a lot of losses in the real world there. Here is number 6.2. Cubic meters of gas at atmospheric pressure is compressed to a smaller volume. See how the volume changed right there? Volume 1 is 0.2 cubic meters, and volume 2 is 0.008 cubic meters. So we really mashed the air down there. The compression is slow, and the process is isothermal. T1, we don't know what it is, but it's equal to T2. And that's good to know, that the temperature does not change. Maybe I should have drawn those over farther, but it's not going to let me now. We've got one more number here. This atmospheric pressure is P1, and that's at atmospheric pressure. So it would be okay here to go 1 atm. Alternatively, you could go 101,300 Pascal, and that would work. I'm going to do this in atmospheres. You could always convert it at the end, but they're asking for P2. Whenever you have those 6 variables, that's ideal gas law. And so that's where we're headed with this one. And I'm going to write down P1V1 over T1 equals P2V2 over T2. And they want P2 right there. So I'm going to multiply both sides by T2 and divide both sides by V2. And I'll get that right there. And you put your numbers in there. Remember that T1 is the same thing as T2, so these guys actually cancel out. We could have done that in the last step, I guess, but we'll have that right there. Here's 1 atmosphere, or 101,300 if you want it to come out in Pascal, which you probably would, but I'm already in. Same 0.2 cubic meters, and it goes down to 0.008 cubic meters. Cubic meters is going to cancel out. We end up in Pascal, and again, you could convert that if you need to. Okay. Number 7, I've got air is going to be heated from this volume to another volume, and there's a couple of things given there. This number is a volume, this number is a pressure. So I've already got V1, 0.044 cubic meters. I've already got P1 equals 1.2 atmospheres. Alright, but we're going to go to 0.058 cubic meters, and this is going to go up to 1.8 atmospheres. And they tell me that the temperature is going to end up at 350 degrees Celsius. And they want to know, what is this? What was the initial temperature? All right. Now, I didn't really get all of my marks just right. This isn't V1. This is actually the volume. And you'd have V1, P1, T1, and so forth. But you can see it's still those same 6 variables. So we're still going to end up with the ideal gas law. And the only one that's really screaming for help here would be that temperature. I can't do this in Celsius. I have to do it in Kelvin. Okay, so I'm going to add 273 there and get 623 Kelvin. We're going to throw that. I'm going to scratch it out just to make sure I don't goof up and put the wrong number. You got to use this one. And when we get an answer, it's going to come out in Kelvin, and you probably want to put it back in Celsius because that's what it started in. But the ideal gas law's got to be done in Kelvin. All right, so that would be the big gotcha right there, Kelvin. Okay, we're looking for T1 right there. So I am going to multiply, you essentially just cross multiply here. You get P1 V1 T2 equals P2 V2 T1, and you can divide by these two guys. I'll just put them on the bottom over here like that, and you stick all the numbers in, and that should come out just fine. You've got them all there. Everything's good. The big question is, what about these atmospheres? The answer is you could leave them in atmospheres, or you could put them in Pascal. And let me just put the units real quick here and show you why it's okay to leave those in atmospheres. P1 here is in atmospheres, V1 is in cubic meters, and T2 is in Kelvin. And then down here, P2 would be in atmospheres, V2 is in cubic meters, and you see how the atmospheres cancel and the cubic meters cancel. You're left in Kelvin. Okay, so even if these weren't in cubic, if these were liters, here it would be okay to leave it in liters and do it. Sometimes, you just got to watch the units, and you're always safe in cubic meters and pascals. If you have any questions, just put it in pascals and in cubic meters. But you can do this kind of thing. Say, would it be all right to just kind of take the easy route and not change them? In this case, the answer is yes. All right, here is a steel rod. It's 2 meters long. So I'm going to draw that just to help me picture it there. That's at 20 degrees. And would look like that. I'm sneaking a peek down here at the thing, and I see that that's in Celsius also, so I'm not going to worry about changing that to Kelvin. The unit's not suggesting that I do it. I also know that this is an expansion, and that's a delta T, and delta T, it's the same in Celsius and Kelvin. If it changes 15 degrees Celsius, it's also going to change 15 degrees Kelvin. So it doesn't matter when there's a delta T. But what we want to do is find a temperature that's going to make this thing a little bit longer. It's going to make it that much longer, 0.003. It started out right there, and then it got a little bit longer. Okay, so I'm going to write delta L equals 0.0003 meters, and you see where this is going, right? Delta L equals alpha L naught delta T, and all we got to do is solve this thing for delta T right there. So I'd have delta L over alpha L naught equals delta T, and probably the easiest thing is just go ahead and solve for that, and then you could you know, add that to the 20 degrees. But let's see what happens here. Delta L is 0.0003 meters. And down here I've got alpha, which is 12 times 10 to the negative 6 per degree Celsius. And the L naught was 2 meters long. So 0.0003 divided by 12e negative 6, also divided by 2, is 12.5. And that's going to come out in degrees Celsius. Shoot. Okay. The meter on top cancels the meter on the bottom. This is the only unit left, and it's on the bottom of the bottom, so it inverts and multiplies up. I need a change of temperature 12.5 degrees. I started out at 20 degrees. That change of 12.5 means that I ended up at 32.5 degrees Celsius. Okay. Here's a window. Got heat going through the window. This is conduction. Right there's the word conduct to kind of help you out where it's going. You got a formula for conduction. You write it down. Looks like that. Let's see what they want us to do. Find the cooler outside temperature. It's another delta T problem. What's the temperature difference between inside and outside? So I'm going to solve that for delta T. And you know what, actually I'm going to leave that T here, that guy, and then divide both sides by K and A. Let's put it in this order, like that. When I go looking at these numbers, I see that 300 joules per second. Joules would be a measurement of heat, Q, and S is seconds, that's time. So that number right there is really Q over T all by itself. This is a package unit right there, and its value is 300 joules per second. The thickness of the glass is 0.3 centimeters. Looking at the unit here, look how the K value is joules, centimeters, second, degrees Celsius. See how that's centimeters? Everything's in centimeters. Let's see what happens if I leave it in centimeters. D is 0.3 centimeters. And then down here, I already taken care of the T. That was with the Q over T, this number. But I need K, which is going to be 0.0105 joule per centimeter second degrees Celsius. And a area. So that's going to be 20 centimeters times 40 centimeters, length times width, to get the area. Okay? And unit-wise, this is going to work out just fine. You can see there's a centimeter on the top, right there, and a centimeter on the bottom. And then I've got this centimeter and that one that are going to cancel. Stop that. This one and that one cancel. I got a joule here and a joule there and a second here and a second there. Here's a degree Celsius, which is on the bottom, so that's going to invert and multiply and give me something in degrees Celsius. And you'd have to get your calculator out to see what that's going to be. But nothing tricky there about that. Oh, you can't even see the top of that, can you? All right. 300 times 0.3, multiply by anything on top, divide by anything on the bottom. 0.0105 divided by 20 and divided by 40. Because those units worked out, I would just leave everything like it was. You could convert everything, but you know what? If it works out, let's go with it. 10.7 degrees Celsius is the change. Remember, we were solving for delta T. So that is my change in temperature. They specify that it's colder outside than inside. The inside is 18, so if it's 10 degrees colder, that would be about 8, right? A bit less than 8. So here's 18 minus 10.7. You'd have to borrow and all that, and you'd get a 7.3 degrees Celsius outside. All right, next. Number 10, how much heat has got to be added to a block of ice? Why is that there, and how do I get rid of it? Well, we're just going to have to make this up. How much heat is going to be added to a block of ice at -7 to turn it into 103 degrees steam? This is one of those multi-stage problems, so I like to have a little picture to refer to here. Starting off with ice, I got 4 kilograms, -7 degrees Celsius. I know that the first thing I got to do is take that -7 up to 0, and it's still going to be ice. And then I'm going to have to melt the ice into a puddle. That's still at 0 degrees Celsius. And then I got to warm that up to the boiling point. So I'll have 100-degree water. And then that needs to turn into steam. You can find better pictures if you don't like mine. That's fine. It's just whatever helps you out. And then I want to change the temperature up to 103 degrees. Okay. Right there, I'm changing the temperature. Sensible. This one's sensible. This one's sensible. Anywhere I'm changing the temperature is a sensible heat change, and these other two are state changes, going from solid to liquid and liquid to gas. Okay. Once you have that, then it's not too hard to get this thing right. Other than the units, just make sure that you got the units right. But here a sensible heat change would be MC delta T. The latent would be ML. Sensible for step 3. Latent is ML. And sensible would be MC delta T again. If it helps you, by all means, then put in some subscripts here that'll keep all this straight. Here I need to use the specific heat of ice, and here the specific heat of water, and here the specific heat of steam. And this is going to be the heat of fusion, and this is going to be the heat of vaporization. Okay? So, you're welcome to use those. You got to look back at your picture and say, my delta T is warming up 7 degrees, and here's warming up 100 degrees, and there's 3 degrees, and that's going to go in these delta T's. So it's a matter of bookkeeping to keep all this straight, but you can do this. It's not that bad. Here is 4 kilograms, and I got to put in the number. All these numbers again to be given. I want to say that's 2090, and then here I've got a change of 7 degrees. Well, I was leaving out the units just because I'm short on space here, but I would encourage you to put them in there and make sure that they work out. This one is 335,000. Here I got 4. I'm talking about water now, right? I'm at this point. And water is 4186, or 4 or 7 or somewhere in there. And it goes from 0 to 100, so that's 100 degrees Celsius. And then I've got 4 kilograms, which I have to take from water to steam. I got to boil it. And that takes a chunk of energy right there. 2,256,000. I'm doing this by memory, so that number may be a little bit off, but somewhere in that ballpark. And then, come on, right there. I got to do this last step, which takes it up 3 degrees. Got 4 kilograms of steam at 100. I got to take it up to 3 degrees. I want to say that's 2090, or I'm sorry, 2010 there. That might be off too. Okay. But I got 1, 2, 3, 4, 5 arrows, and I got 1, 2, 3, 4, 5 times that I add heat. You push the right buttons and you will get the right number on that, like that. All right, I'm going to leave that as an exercise to the gentle readers, and we'll move on here. Number 11, all they want you to do here is to draw the 4 processes. I want you to have a clear picture that an isochoric process goes either straight up or straight down. The volume is locked in at 2 liters or 4 liters or whatever the number is. And the pressure can go anywhere it wants, up, down, whatever. If I add heat, it goes up. If I pull heat out, it goes down. But the volume never changes, so it's a vertical line. That would be line A. For B, it's isobaric, same pressure. Here's the pressure, and it is locked in right there. It can go expand in volume, it can shrink, it can go left or right, but it cannot go up or down. So that's line B. Isothermal means we're keeping the same temperature. As that expands, then the volume expanding would be going to the right, but my temperature is not changing, so the pressure's got to drop, and it kind of does that. Line C. And the adiabatic, right there, I'm not even adding any heat, so it's going to drop faster, and I get a line down there. And that's all that one wants you to do, is to be able to associate those shapes of the 4 processes on the PV chart. Right here I've got an engine, and I'm going to put in 500 joules of heat. It's producing mechanical work, and the internal energy changes by 160. How much work do we do? Interesting. Let's figure out what these numbers are. This is the trick on all the physics problems, right? 500 joules of heat. My symbol for heat is Q. And then they tell me that the internal energy changes by 160. Oh yeah, that'd be delta U equals 160 joules. And they want work. Oh yeah. You know, usually if you just kind of list out all your variables, then you'll see the association with those, and you come in here and say 500 minus 160, and that's what, 340 joules of work. There we go. Okay, that's all they want you to do right there. Okay. They did not ask for this, but it would be real easy to come up with the efficiency, which is just Q over W. If I get 340 joules of, I'm sorry, I got that backwards. Let me do that again. How much work did I get when I paid for some heat? I got 340 joules of work when I paid for 500 joules of heat, and that would be 68%. 500 multiply the bottom by 2, you got to multiply the top by 2 and move your decimal places and stuff. 68% right there would do that. So here's number 13. Find the average speed of an oxygen molecule. We did this one on the video, right? If this thing is moving, and remember oxygen's kind of like this, it's got 2 oxygen, there's a double covalent bond there, blah, blah, blah. That's chemistry stuff. Who cares? But anyway, if this thing is moving with a velocity, it's certainly got mass, it's got kinetic energy. And we have 2 ways to calculate the kinetic energy. They have to be the same number. The old way was 1/2 mv squared. And Boltzmann came along and said, well, gee, guys, I figured out that it's related to the temperature. And the higher the temperature, then the more the kinetic energy, the average kinetic energy of the gas. And so if we just set those equal like that, they want the speed, the average speed. Here it doesn't say velocity because velocity is a vector quantity. So, you know, one moving left and one moving right would be 2 different directions, blah, 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 up, down, all that. We just want to know the average speed. So that's why it's specified that way. I'm going to let these 2's cancel out. I'm trying to get V by itself. Let's divide by M. V squared equals 3kt over m, and when I take the square root of both sides, I would have the square root of 3 kT over m, like that. And we could put the numbers in and get that. It's usually a pretty spiffy speed. It's 400 or 500 meters per second, something in that ballpark, 2, 3, depending on the temperature. But a couple hundred meters per second, which is pretty impressive. Now, you should know that this is translational kinetic energy here, and we said it's all in just motion. In real life, we would also have rotational energy, where that molecule is twisting around its center point, and we'd probably also have some vibrational, where this thing is going back and forth, right? This guy's doing this. It's like two balls on a spring going boing, 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 back and forth. So in real life, you got more going on. You would also have rotational kinetic energy and vibrational kinetic energy. But we're not worried about that, all right? This is just the ballpark number here, and good enough for what we're doing. All right, number 14. Got this little picture at the bottom. These last several problems go work off of that. So let's see what happens here. We're going to start at A, go up to B, down to C, and back to A. That makes a cycle. We are going through the same process over and over right there. And they give us some numbers right here that we can refer to for these last several problems. The energy at point A, the energy at point C, the volume at A, the volume of B. That's the same number because see how the volume's locked in. I got an isochoric process right there. That's good to know. VC is bigger because it expanded, right? Went straight up, didn't change the volume, but then the volume did expand. I got some work out of that. So this thing did some work for me. And then I got to do some work to push it back so that it can go through the cycle again. But I get a little bit of work every cycle out of this thing. So I keep running the car engine or whatever, the tractor engine, whatever this is. And every time I get a little bit of work, it adds up, and I get a big amount of work, right? So let's see what happens here. We want to find the work from A to B. Oh, that's funny, isn't it? A to B is isochoric. Okay. How much work do I get out of an isochoric? Work equals 0. If the volume doesn't change, if it's straight up and down, my volume's not changing right there, then I didn't move it. You remember that work equals force times distance? My distance is 0, man. Nothing happened. So my work is 0. And that's all they want right there. Here's the next one. Where are we going? From B to C. Oh, let's see. If 20 kilojoules enters the system along the path from A to B, what's the internal energy at point B? I'm going to blow this up a little bit and make a little bit better picture. Here's point A. Here's point B. They tell me that at the bottom I've got 30,000 joules. The internal energy at point A is 30,000 joules. And now they tell me that I'm going to put 20,000 in. So delta U equals 20,000 joules. There's only two places that, well, that's actually the heat, isn't it? I'm sorry. It'll be the same number, but right here, Q. The heat is 20,000 joules. I built a fire in this thing, and I heat it up with that much energy. You remember there's only two places that heat can go. It can go into the change of internal energy, or it can go into work. We've already said the work on an isochoric process is 0, so it all goes into the change of energy. This is the change of energy. That's where I was leapfrogging to. But if they want the energy up here, I started with this much, I added that much. Up here I have 50,000 joules of energy. So that's the number that they want for number 15. Number 16, we've got an adiabatic process from B to C. Right here over to right here. We just found this was 50,000 joules of internal energy. And this is now telling me that UC, it told me before, but I didn't need it before, so I didn't mention it. There's 38,000 joules at point C. Okay? If the process is adiabatic, find the work done by the system from B to C. So here's the first law of thermodynamics. I like to go here first because this is just such a simple idea. You put some heat in, it either makes it hotter or it does some work, right? It changes the internal energy or you get some work out of this thing. All right. Well, in an adiabatic process, Q equals 0. You're not adding any heat. So if I get 0 equals delta U plus W, and they want the work, then the work is equal to the loss of internal energy between those 2 points. If I end up at 38,000 joules, and I started at 50,000 joules, that would be my delta U. I had this little negative sign in front right there. That was from the formula. I want to do the final minus the initial here. Went from B to C, so I'd have to get it in that order. And that's going to be the amount of work. I believe you're going to find that's a negative 12,000 or positive 12,000 joules of work right there. All right. And I think this is the last one here. Consider a system that's along this. Find the work from C to A. I'm interested in this path right here. Okay, and we're actually going backwards on this thing, but I see that it's flat. I see that the pressure is constantly this number right here, so I know it's an isobaric process, and I know that in an isobaric process the work is equal to the pressure times the change in volume. Okay, well, my pressure at point A is 2 times 10 to the 5th Pascal, and my volume, remember here I need final minus initial, and in this case my final is going to be the volume at point A, so that's 0.02 cubic meters, and the initial was the volume at point C, 0.05 cubic meters. That's negative 0.3, and I multiply that here, I'm going to get, I think it's 6,000 joules. Remember that Pascal is a Newton per meter squared, and then I'm multiplying that by cubic meters, so the meter squared cancels 2 but not 3. I've got a Newton meter, which is a joule right there. Okay, and since this comes up negative, then I should have a negative right there, and that negative means that I have to do work to compress the cylinder back so that it can do this thing again. In your car engine, you personally don't do it. The motor does it. The motor has to compress that gas, and you've got a big flywheel that has enough rotational momentum to keep the motor going to do that work right there. But it takes it out of the system, right? You're losing some work right there when the engine has to do it to reset it. Yes, that is the last one. Thanks for tuning in. Hope that kind of helped. I'm always available with for questions, and just let me know what you need, and I'll try to fix you up. All right? Thank you much. Have a good day. Best of luck on the test.